All right. Okay, what's our first step going to be?
Snapshot values.
Snapshot values. Okay, I'd sort of recommend maybe a picture too. Okay, so we've got a 10-inch diameter spherical iron ball. Okay, so that's going to be okay, and it's coated with a layer of ice of uniform thickness. Okay, it doesn't tell us how thick the ice is, though. Right? It's all right. Don't need to know. So something like that, right? So there's the coating of ice on the outside. Okay? So what do we know here? Let's label some stuff. So this distance right here is 10's the diameter, so that would be 5. And then what do you want to call this distance here? You could either call this some distance, or maybe we call the whole thing R. Maybe we say something like from there to there is R. Okay? So when the radius is, we want to know when the radius is 7 in this case. Does that make sense? The radius of the ice ball, right? Clear to the center of the iron. Does that make sense? Questions?
The radius is 2 inches, or
Well, then we want to know how fast is the thickness of the ice decreasing when it's 2 inches thick, when the ice is 2 inches thick. So if the radius of the iron is 5, and if the total radius, what we call R is 7, that would be when the ice is 2. Does that make sense? I mean, that's not the only way to do it. It seems to me like that would be maybe an easy way to do it, though, because R is a really natural variable to use, right? Because we're talking about a sphere. So then, what are our snapshot values? So that's step 1. And really pay attention here. Keep in mind, on the open-ended paper and pencil test, I don't really care what your answer is. It's different than the other kinds of tests. On that test, I don't care. You could get the wrong answer and still get full credit if you do all the work completely correctly, right? So, but conversely, if you just have a right answer on that and no work, it's worth nothing to me on the open-ended one. I don't care about the answer. I want to be able to see the process, right? So you have to be able to organize the process. So step 1 is snapshots, right? So what are our snapshot values?
R.
Okay, so R is, we're saying 7, right?
V dot is 13.
Okay, there we go. We know ice is melting at a rate of 13 cubic inches per minute, so those are units of volume over time. So we know V dot is what?
13.
Is it 13? Okay, but is the volume increasing or decreasing?
Negative
Oh.
13.
Okay, it's decreasing. Everybody see that? So it's negative 13 in standard units. And then what are we looking for?
R dot.
R dot. Everybody see that? Because if we're asking the question, how fast is the thickness changing, isn't that the very same rate at which the radius is changing? Hypothetically, let's say that the radius we're changing at a rate of 1/4 inch per minute. I mean, the thickness was decreasing at a rate of 1/4 inch per minute. Well, wouldn't the radius also be decreasing at 1/4 inch per minute then? Everybody agree? Okay. So it would be probably easier to couch the question in terms of R dot. Okay? Questions? That make sense? Okay, there's one way to do it. So now what's step 2?
Like the parent equation.
Parent equation. Okay, what's it going to be here? That's a volume equation. Good. Good. So the parent equation V equals 4/3 pi r cubed. Okay, next step, okay, differentiate implicitly. Good, so we're going to implicitly differentiate with respect to what? What variable? No, t.
T.
Good. Okay, with respect to t. And what's that give us then? First term is,
4 pi.
well, what's the left side gonna be? V dot equals,
4 pi r squared times r
good, everybody see that?
naught.
Because now where'd the 3 go? Well, because 4/3 pi is a constant, what's the derivative of r cubed gonna be with respect to t? Well, I've got 3r squared, and the 3 cancels the 1/3, right? And then I end up with an r dot at the end too, because there's 2 layers. I'm differentiating with respect to t, not to r.
So
Right.
when we're differentiating in respect to t, we'll always have like some value, the r dot.
Yes, yeah, we're always gonna get a dot, aren't we, when we by chain rule?
And we know that it's with respect to t.
Because of the way the questions, the way the question's phrased here, we want to know how fast is the outer surface of the ice decreasing. Well, look at this rate up here. It's given to us in terms of minutes, right?
So when we differentiate, is it always with respect to t?
Yes, yes. I mean, I hate to say the word always, ever, but it's, I mean, if you think about a related rates problem, typically, like, you're trying to look at the rate at which something is changing with time. It's really rare that it would be something different. I don't think we've had any examples where it's been different. Laura, did that make sense? Did this part make sense how we got there?
Yeah.
Okay. So then there's step 3, right? Now we're done with the calculus, and now we're just to the plug and chug stage, right? So now we're just gonna say, we're trying to find r dot, so we'll isolate r dot algebraically. So now we isolate r dot. R dot would just be v dot divided by all that stuff, right? Okay, and then if we plug in numbers, what do we get? What are our values here? So we get over 4 times pi times 7
Yeah.
squared, so whatever that is. They want it as, I can't see how they expect the answer to be. Do they want it as a decimal on this one? Or do they want it? Exact answer, okay. So then we'd end up with negative 13 over, yeah, 200 bucks, yeah, so 196 pi. That's our exact answer. What would the units be? No, how
Inches
fast?
per minute.
Oh, you know what we did though? We answered the wrong question, didn't we? No, okay, we answered this one. How fast is the thickness of the ice decreasing? So what would that be? It'd be, it'd be negative is correct, but what would the units be? Inches per minute.
But because it's decreasing, it keeps asking for a positive.
Oh, I got you. I see what you're saying, yeah. They want to know, okay, so the wording says, how fast is it decreasing, right? So if they're already saying they know that it's getting smaller, what's the rate at which that's happening? So do you understand that that answer is actually supposed to be positive? Whenever you ask for how, well, it'd be like saying, what is the deceleration? How fast is a car decelerating? Or what rate is a car decelerating? Yeah, the acceleration's negative, but you'd say it's decelerating at a rate of 5 meters per second, right?
Yeah.
That's a little, if you're unsure about that, I can see where that part's a little tricky, so ask me. This is the answer, but your answer, you just want the absolute value of that, right? You want the magnitude of the rate, okay? What about part B? How fast is the outer surface area decreasing? What would you do there?
Differentiate
pair.
Okay, good. So you've got, really, you've done most of the hard work already, right? The only difference is now the parent equation you'd be starting with would be the surface area equation instead of the volume equation, right? So now we come down and say, okay, for part 2, S equals 4 pi r squared. So S dot equals what? 8 pi r dot, and we know all those now, right? There's r dot. We know what r is. R is 7. And so we can solve for S dot. Okay? Make sense? Okay, I'll make sure I put these notes up tonight. Yes, sir.
On the test, are most of them gonna be about spheres?
It's gonna be pretty random.
Wait, so how do you know what S
Yeah.
is?
How do we know what S dot is?
Never mind.
Okay, what?
I like spheres.
You like spheres?
That would be a lot easier.
Yep. Is there a password?
Oh, I don't know, I didn't check it.
No, it shouldn't be. Shouldn't be. Yeah.
I always.
So how about, which one was the kite one on? Okay, so what about this one then? We want a picture. So a child flies a kite at a height of 90 feet, the wind carrying the kite horizontally away from the child at this rate. Okay? How fast must the child let out the string when the kite is 150 feet away? So this is just a triangle problem, isn't it?
Yeah.
Okay, so we've got, yeah, something like this. So,
Are there 2 practice tests? Wait, where is it?
One's from last year, so you can even.
there is one from last year?
The bottom end is where the child is, the one going up is the height.
But wouldn't it work with that?
Yeah, I guess.
Okay, so there's, we can label some things here, right? So here's the child down here, here's the kite, right? So then this is just 90. Let's call this X, I guess. Sound good? And we'll call this,
Is it 150?
no, that's this distance, right?
Oh.
Okay, but that's a variable, right? Now, this is something kind of important. When I'm drawing a picture like this, everybody just take one quick second, even if you're doing something else, because we're going to come back to this again. But this is kind of important. When I'm drawing a picture like this that represents a calculus situation where things are changing, it's not static, right? The kite is actually moving in that direction, right, away from the child. Why do I put a 90 there, but a variable there?
Because it's not changing.
Because it's not changing. If it's a constant, you can label it with a number. You should label it with a number. But I don't want to put a 150 there because it's changing, right? Let's call this D for distance, how about, right? And so now there's our picture. We're going to write down some snapshot values of the variables, right? But that's 90 always, okay? So then what are our snapshots?
What problem is it?
This is number 4 on the second problem set. Okay? So what do we got here? What's this? Which rate is that? If the wind is carrying the kite horizontally away from the child at a rate of 30
X dot.
So it's X dot, good. Okay. So X dot is positive or negative? Positive 30, okay, and the units are feet per second. How fast must the child let out the string when the kite is 150 feet away from the child? What value is that? D, yeah, because that's the distance of the kite, right? So we want to know when D is 150, which value are we looking for? Which rate?
D dot.
D dot, because this is actually the string right there, isn't it? Right? Okay? So there's step one. What's gonna be our parent equation? Yeah, it's Pythagorean theorem, isn't it? This is just a right triangle. And so we get d squared equals x squared plus 90 squared, right? Okay. And so then if we differentiate implicitly, what do we get?
Equals
2d
D
dot equals 2x x dot, so I can cancel the 2's, right? And then if I solve for d dot is just x dot over d, right? Make sense? So what are my options here? Because if I look at the, plug and chug part now, I know x dot and I know d, but I don't know x.
So you put D into it.
Sure. So I could, one perfectly reasonable thing to do would be to say, let's add another snapshot value then, right? Because we know our snapshot is when d is 150, right? So then x would just equal, so x squared plus 90 squared would have to equal 150 squared. So x would equal the positive square root of 150 squared minus 90 squared, which is, what is that going to be? So it's what, 3, so it's going to be 120, yeah. Okay, makes sense? So x is 120. So then we can just plug that stuff in and get an answer. Okay? Good, so we end up with 120 times 30 over 150, so we can do that. We could do, actually, do this. Okay, no, let's just do that. And then, what's that gonna give me? 24. And what would the units be? Feet per second. Yeah.
That's weird. I have different values, but I still got 24 feet per second.
Really?
Yeah.
Weird. Weird. About that. Okay. And then I might even do you guys one favor here. Yes, I really like this problem. It's a cool problem. So as a spherical raindrop falls, it reaches a layer of dry air and begins to evaporate at a rate that is proportional to its surface area. So S equals 4 pi r squared, I'm giving you that. Show that the radius of the raindrop decreases at a constant rate. Okay, how are we going to do this? This is actually, there's very little work to do here. So what's this mean? If it's evaporating at a rate proportional to its surface area. If it's evaporating, it's losing volume, isn't it? Right? Because the volume of the water from the drop is being dissipated, right? The actual volume of the drop. So we could say then, let's take this statement. How am I going to say this? Evaporate at a rate proportional to its surface area. So V dot is proportional to surface area, right, which is 4 pi r squared. That's proportional to sign, right? Now think back, what if we say something is proportional, how do we write that as an equation? If y is proportional to x, how can I write that as an equation? Y equals, I think algebra, I was probably algebra 2 stuff more than anything. What? Something like that, where K is the constant of proportionality. We don't know what it is, but it's gotta equal some constant times X. If K is 2, then Y would always be twice as big, but they would change proportionally, right? If K is 1/2, then X would be twice as big, but they'd always be proportional, right? So then this becomes V dot equals K times 4 pi r squared, okay? So that's a true statement. Well, we also know that if we start with the parent equation, let's look at this differently. We start with the parent equation, volume equals 4/3 pi r cubed, and I just implicitly differentiate with respect to t.
It equals
Aha, then I'm gonna get
so K is-
V dot equals 4 pi r squared r dot, right?
So K is-
Aha, so, right, so look at this then. If we know that by just doing calculus, by implicitly differentiating and relating these rates, this is always true for any sphere that's changing volume, right? Okay, in this particular case, they're telling us that the rate of evaporation is proportional to surface area. So for this case, that is also true. Well, look at this, what we got here then. If I have an expression for V dot and another expression for V dot, those must be equal, right?
So K is 1/2.
So then we can say, look what happens here. If I set these equal to each other, I get 4 pi r squared times K equals 4 pi r squared times r dot. So what's r dot equal to?
K,
Okay, we don't know what K is, but what do we know about K?
it's constant.
Well, it's what? I thought I heard it.
It's a constant.
It's a constant. So if r dot equals K, then didn't that just show the radius of the raindrop decreases at a constant rate? Yeah, r dot is constant. Right? That's, and doesn't that have to be the case? I mean, I like stuff like this because it's true. I mean, what else would the rate of evaporation be proportional to? Where does the evaporation happen? On the surface of the raindrop. So it has to be proportional to the surface of the raindrop, doesn't it? Right? That's the only thing that really affects it. And so, yeah, we just showed, that's just amazing. Just a little bit of math there, we just showed that has to be true, that the radius of the raindrop has to change at a constant rate. I just love stuff like that. All right.